class.
Hi, everyone. Thanks for being here today. My name is Matt Stanley. I'm a professor of the history of science at New York University. And we're all here today to talk about Isaac Newton. I think it's helpful to get a sense of who Newton was in terms of his personality before we sort of get into the details of his life. And there's a particular experiment he ran that I think helps sum up what's unique about his character. So at one point in his life, he's studying colors. And as he often did when he was investigating something experimentally, he would find all the different ways that thing appeared and study them in sort of all the different manifestations. So when he's studying colors, he looks at rainbows and prisms, but also dyes and paints, and then really strange things. Like, for instance, you notice that if you press slightly on the edge of your eyeball, don't do this, you'll see strange colors appear on the other side. And he began to wonder if it mattered where you pressed on your eyeball. So in addition to pressing on the side, he also takes a dagger and slips it behind his eye so he can press on the back of his eye to see if the colors are different. So when you're wondering what kind of a person Isaac Newton was, he was the kind of person who would stick a dagger inside his own eye just to get one extra little detail on his experiment. That's the kind of person we're talking about today. Newton is born a sickly child on Christmas Day, 1642, in Woolsthorpe, a small town in England. His home was in the middle of apple orchards. That's sort of the local industry in Woolsthorpe. His father dies before he was born. His mother remarries right away. And generally, he has an unhappy, mostly neglected childhood. We know he goes to school at age 12. We really don't know what he studied, though. He's known in the town not as a particularly good scholar, but rather as a strange little boy who builds things. He makes inventions and gadgets, lanterns that won't blow out in the winds. He was known for this little cart he had built, so sort of hand-powered, where he would zoom around town. So known as sort of a sickly, strange child without many friends. And he is strangely introspective in all sorts of different ways. So for instance, in the summer of 1662, he had some kind of a religious crisis. He became very concerned about the state of his conscience. And we know this because he kept a journal of his sins. He wrote it in code. We've cracked the code since then. And his sins include all sorts of interesting things, like making a mousetrap on a Sunday and making pies on a Sunday night, putting a pin in John's hat to prick him. But some of them get a little more serious, such as threatening my stepfather and mother and threatening to burn them to death and destroy their home, wishing death on people and hoping it would come to them, striking many people, punching my sister. And then things like being peevish and not loving God for himself. And of course, the worst possible sin of reading the history of the Christian champions on a Sunday. And this is all to indicate the kind of self-disciplined, puritanical lifestyle that he develops and really comes to be indicative of the way he thinks and works for his entire life. As he becomes older, he goes to University of Cambridge, specifically Trinity College, to study. And when he's there, he has what nowadays we would call a work study. That is, he earns his room and board by acting as a servant for the wealthier students. Now, this is kind of strange because his mother actually had plenty of money, but she apparently just didn't want to support him. So forcing him to work probably did not help their already relationship. Newton didn't get much out of the classes at Trinity. And indeed, as near as we can tell, he attended very few of them in person. And the reason for this was probably that the classes there were still focused on the Greek and Latin classics. So for instance, specifically, physics and astronomy, what Newton was interested in, was still using the Aristotelian cosmos. So Aristotle's idea that the way to think about the universe was that the universe, of course, was all centered on the Earth, And the things that happened here on the surface of the Earth were completely different from what was found elsewhere in the universe. That is, the celestial bodies were completely different kinds of things that followed different laws and rules. And this is the view that essentially had dominated European thought for just about 2,000 years by the time of Newton. So by the time Newton goes to Trinity, the work of Copernicus, Tycho Brahe, Kepler, and Galileo had all shown that Aristotle's system had fatal flaws, but there was no real substitute. So it was still taught as sort of the default way to think about the physical world. So even with this classical emphasis, even if the classes were dull, the university was still an intellectually exciting place for Newton. And we know this because we have his notebook that he kept while he was a student. And we can see here one of the early pages from that. And it's an interesting book because the front of the notebook is the notes he takes in his classes and in the books he has to read for his exams. But then he flipped the notebook over and started taking notes on the back of the things he was actually interested in. So it's this great sort of thing where there's the required work in the front and then the things he's actually excited about in the back. And you can see how he flips back and forth between those two. And what he's particularly excited about at the time is what was known as the mechanical philosophy. This was largely based on the ideas of Descartes. And this was the premise that you should think about and find explanations for the physical world based on mechanical interactions. That is, imagining that the world is made of little pieces of matter, what nowadays we would call atoms, that bounce off each other in mechanical ways. And Newton is approaching all of this in sort of a spirit of genuine inquiry. He's really interested in new possibilities, finding out what the consequences might be of a given idea or theory, and then figuring out some way to put it to the test. So this is a particular thing that really marks his work for his entire life, is finding some experimental way to test any kind of abstract theory that someone might come up with. He's particularly interested in mathematics. He's almost completely self-taught in this. This is not a subject that was particularly well taught at Trinity at the time. And it's important to remember that mathematics at the time also included what nowadays we would think of as engineering, that is building things and working with his hands. And this is a second-class kind of knowledge at the time. The Aristotelian hierarchy of knowledge put philosophical understanding as the most important, and then mathematics lower, again, because it involved working with your hands, and anything having to do with the body was less important than things that were purely mental. So as you can probably see from the kind of calculations here, Newton was extremely good at having intense focus on whatever he was working on. He would dedicate all of his energy, his entire being, to cracking some specific aspect of a problem. He often forgot to eat. He would work for days at a time without taking a break. Sometimes he would write standing because he simply forgot to sit down. He couldn't take that much time. He would forget to feed his cat. We have his roommate complaining that he's constantly having to feed Newton's cat because Newton is too busy working on a particular problem. And it probably shouldn't surprise anyone that he had very few friends, really no real colleagues, and essentially no one knew the kind of work he was doing. Come 1664, he receives his degree. He's able to stay on at Trinity on a fellowship received under some kind of mysterious circumstances that we don't quite understand. But it's soon after that when everything changes, and that's when the plague arrives in Cambridge. And essentially, the University of Cambridge closes because of the pandemic, and he has to go home to essentially do remote learning, or whatever the 17th century equivalent of that would have been. So he goes back to Woolsthorpe and sits in the apple orchard owned by his mother. And now that he's finally undistracted by, say, classes and professors and the things he had to do at Cambridge, he's able to just attack the problems that he's interested in, essentially one after another. And this period from the summer of 1665 through 1666 is sometimes called his miracle year. He starts with mathematics, and he wants to tackle sort of two of the great unsolved problems of 17th century mathematics, both having to do with mathematical curves. So one of them is if you take some given curve of a parabola, say, and you want to calculate the area underneath it, that was extremely difficult to do. Nowadays, we call this the problem of integration. The second problem is, again, for any given curve, what's the tangent to that? This is the problem of differentiation. And these are problems that could be solved easily for very specific circumstances, say a circle. But what Newton wanted was some kind of method that would let him do this for any kind of curve. So he develops an entirely new form of mathematics that he calls his method of Fluxions. And he solves this problem to his own satisfaction and moves on. And this is when he sits under the legendary apple tree. So this is the source of the apocryphal story of Newton either seeing an apple fall or the apple falling on his head. Neither are true. But we do know from his own telling that he is sitting in the orchard when he starts thinking about problems of motion and movement and gravity. So as he tells the story, he sees a force that an apple hangs on the tree and it's clearly being pulled down by something. And he also sees the moon moving through the sky night after night. And he begins to wonder whether those are the same kinds of forces. So something stirs his interest in this question of how bodies here on the earth relate to the bodies up in the heavens, and in particular, how force and motion are manifested. We don't know precisely what kind of conclusions he came to that first summer, but we do know that he felt that he had solved the problem. That is, whatever conclusions he came to were the final ones he was interested in, and he moved on to his next subject, which was optics, the physics of light. He's interested in colors. This is when he performs that awful experiment with the dagger I talked about at the very beginning of our time here. So he's interested in prisms and rainbows, and again, decides he had cracked optics and solved all the interesting problems and moved on. So within this 1 year, his miracle year, Newton tackles the three greatest scientific problems of the 17th century, these mathematical curves, the movement of bodies, the behavior of light, and he decides that he had solved them completely, and he moves on. After that year, he returns to Cambridge, but he doesn't tell anyone about all the work that he has done. He's more than happy to just have solved these problems to his own satisfaction. This changes somewhat when he uses his new theory of color and optics to build a new kind of telescope. It's called a reflecting telescope. Previous telescopes of the sort built by Galileo and Kepler were called refracting telescopes, and those use lenses. Newton's new telescope was called a reflector, uses a mirror instead of a lens to get the same kind of optical effect. This is the actual telescope he builds in the 1660s. It's quite small, it's about yay big. If you find yourself in Cambridge, you can go to the Whipple Museum of History of Science and see it yourself. And this is a telescope that solves certain problems with existing telescopes at the time, and is also much more powerful than all the ones that were available at the day. Now, word about this telescope does get out, probably because he has to go outside to use it so other people can see it and see what's going on. So word of this gets down to London, to the Royal Society, which was one of the new scientific societies of the day, in some sense, the very first scientific organization ever. And they invite Newton to come down to London and demonstrate this new telescope for them. And they are amazed at what they see. This is an extraordinary piece of scientific equipment. He's elected to be a fellow of the Royal Society immediately, and they ask him to write up the theory of how this new telescope works. And he does that. So he writes up a document explaining his theory of color, describing his experiments with prisms. And the mystery at hand was how white light, say from the sun, gets turned into the colors that come out of the prism. And the prevailing thought at the time was that the prism actually created the colors, that it changed the physical substance of the prism changes the color from, changes the light from white into the different colors. And Newton disagrees. He makes the case that white light is already a composite of all different colors in the way we think about it today. And the prism just split the colors out, but the colors were there to start with. And this is a controversial idea. As I said, this is different than the prevailing theory. And in particular, he starts getting into arguments at the Royal Society with someone named Robert Hooke, who's one of the great experimentalists of the day. He's actually the person in charge of demonstrating experiments at the Royal Society. The question mark here next to Hooke's name is because we're actually not sure this is a portrait of Hooke, and we don't really know what he looks like or looked like. We have a few portraits associated with his name, and the reason for this mystery I'll mention a little bit later. The important thing to know is that Newton is immediately deeply offended that Hooke disagreed with him. He doesn't quite understand how this could be. Newton is quite sure that his theory is simply right and that he had demonstrated that it was correct. And he gets extremely frustrated that Hooke is disagreeing with him, particularly in a public kind of way. So Newton comes up with a whole series of experiments, new experiments, with the prism that are essentially intended just to prove Hooke wrong. Newton calls these his experimentum crucis, crucial experiments that are supposed to decide between two rival theories. And the change that Newton brings into his experimental setup here is he has his initial prism in which the white light is broken into the colors, and then he takes a little bit of that already colored light and puts that through a second prism, and then sees what comes out of that. And he argues that if Hooke is right, that the prism is creating the colors, then you should get a full rainbow after the second prism as well. But in fact, what happens is you only get more intense colors. You don't get a full range of colors again. And Newton says that's because the colors that were originally present in the white light at the start have already been filtered out by the first prism, so they can't get filtered out again by the second prism. So Newton says if you set up this experiment and you look at it, you should be immediately persuaded. And many people are. Many people are convinced that Newton's theory must be correct, but Hooke still disagrees. And Newton is furious about being questioned, and he literally packs up his toys and goes home to Cambridge and does not talk to anyone for about 10 years. This is, again, a really important aspect for understanding who Newton is and how he works. He's really not very interested in what other people think about his ideas. He's happy to have people sort of adore him and praise him for his work, but he doesn't feel any special need to persuade them if they don't agree with him at the start. So back in Cambridge, he again continues to work, but doesn't share his results with anyone. One of his professors and mentors at Cambridge, Isaac Barrow, tries to convince him to publish some of the work he's been doing, particularly his mathematical results. But Newton was so soured by having people disagree with him in London that he refuses. Soon after this, Barrow actually resigns his professorship, the so-called Lucasian chair, essentially in order for Newton to take over that professorship. Barrow was so impressed that with Newton's work that he wanted to make sure that Newton had sort of a secure financial position from which to work. And Newton's job as a Lucasian professor was to lecture on some mathematical topic once a week. He chose optics because that's what he was working on. And his responsibility was to lecture in a particular hall at Cambridge and then deposit his lecture at the University Library. And he does this. So you can go to Trinity and see all of the lectures that he deposits over the years. And we know he lectured. We're also pretty sure that no one attended any of his lectures. So for decades, perhaps, Newton lectured to an empty room and never complained about it. He seemed perfectly happy just being the only person in his own classroom. So after the incident where he returns angry from London, 10 years pass. Newton talks to essentially no one about what he's working on. This changes in 1684 when Edmund Halley of Halley's Comet fame decides he needs a little help with a problem he's working on. So by this time, it had been an entire generation since Johannes Kepler had written down what nowadays we call Kepler's laws, which are three mathematical expressions that describe the way the planets move around the sun. The planets move in ellipses with these particular mathematical patterns having to do with their distance from the sun and how quickly they move around. And the great problem of physics and astronomy in the 1680s was to figure out why Kepler's laws were what they were. That is, Kepler's laws are completely descriptive. They tell you where the planets are, but not why they're moving. So what Halley is trying to do is to start with some general principle, a claim about the kind of forces at work on the planets, and then use those to derive Kepler's laws. And then if he can successfully do that, then there's a sense that he had really figured out what the forces were that were making the planets move. But he couldn't make the mathematics work. Someone suggested to him that that guy Newton up at Cambridge was pretty good at this kind of work, and maybe he should go ask him. So Halley goes and knocks on Newton's door, explains the problem he's trying to solve, and he says, Professor Newton, if you had an inverse square law, a particular kind of force at work, what would the path of a planet be when subject to that force? And Newton immediately says it would be an ellipse, which is exactly what Halley was trying to prove. So Halley says, well, how do you know? Newton said, oh, well, I solved that years ago, probably referring to his miracle year, but I lost the piece of paper I wrote it on. And Halley says, well, it would be really nice if maybe you could rework that, since, in fact, the entire intellectual community of Europe has been trying to solve this problem, and you've already solved it. We'd like to know that. Newton says, okay, give me a little bit of time. I'll get it for you in a couple of days. And a couple of days turn into a couple of weeks, and it eventually takes him about a month. But finally, he sends it to Halley. It's a 9-page document that does everything that Halley had spent years trying to do. That is, Newton is able to show why Kepler's laws look the way they do. He's able to demonstrate why comets have hyperbolic orbits. And Halley is stunned, and everyone he shows it to is stunned. The Royal Society is agog. No one had ever done anything like this before. That is, using one principle to explain all different kinds of motion. So Halley again goes back up to Cambridge and entreats Newton and says, could you please write out your entire system for this? What else do you have hidden here? And Newton says, okay, it'll give me a month. I'll write up a book on this. And a month turned into months, and eventually a couple of years, as Newton becomes utterly focused on writing up the complete version of his system, his general system of motion and forces. Becomes utterly committed to it, foregoing everything else he's working on. And all of this work culminates in his great book, the Principia, as they're called, the Principia Mathematica, published in 1687. It's a weird book for a number of reasons. I think one of the most interesting is that Newton intentionally makes it difficult to read. It's written in the most complex mathematics he can come up with, not because it's necessary, but because he says he doesn't want to be bothered by people who aren't already good at mathematics. He doesn't want them to waste his time. So he sets the bar as being quite difficult to read the book in the first place. And it's a book of staggering scope. It's a set of mathematical principles, as the name suggests, for investigating the motion of all bodies, both here on the surface of the earth, as well as celestial bodies up in the heavens. And it's worth a moment to sort of consider the title here, Mathematical Principles of Natural Philosophy. This is a title that would be oxymoronic to, say, Aristotelian philosophers, because the idea that you needed mathematical principles to explain philosophy wouldn't have made any sense to them at all. A quick reminder that natural philosophy as a category is what nowadays we would call science, and particularly the physical sciences. And it's important to remember that at the time, there's no consensus for how to understand the natural world. So this book has to establish not just the results of Newton's work, but how he got to those results in the first place, the kind of methods that made his science make sense. So what are the basic rules that he thinks we should follow in doing science at all? And he calls these the rules of reasoning. So I'm going to put up excerpts from the actual reasoning, the actual rules, and then try to explain them in slightly more accessible terms. So he starts off by saying we should admit no more causes of natural things than such are both true and sufficient to explain their appearances. So to the same natural effects, we must, as far as possible, assign the same causes. Or put more simply, if it looks the same, it is the same. And he's particularly thinking about motion here. So the motion of, say, a thrown ball here on the surface of the earth in Aristotelian terms would be explained as one kind of thing. And then the motion of the moon through the sky would be explained as a different sort of thing. But Newton wants to say, if it looks the same, it looks like motion, we should treat it the same as well, as being the same kind of thing. Next, the qualities of bodies, which admit neither intention nor omission of degrees, and which are found to belong to all bodies within the reach of our experiments, are to be esteemed the universal qualities of all bodies whatsoever. Or all the stuff is the same. That is, wood in England and wood in France should be thought to be the same things. But also, even substances that we can't touch, like, say, the moon or whatever Jupiter is made of, should be thought of as the same kind of stuff. Again, this is completely different than the Greek approach, which was to think that the heavens were quite different than what the surface of the earth is like. Then, in experimental philosophy, we are to look upon propositions inferred by general induction from phenomena as accurately or very nearly true, notwithstanding any contrary hypotheses that may be imagined, till such time as other phenomena occur by which they are made more accurate or liable to exceptions. It says all the laws are the same. So that is the laws of nature. So in addition to the substances, the stuff of the universe being the same everywhere, the rules, the phenomena that happen are also the same. And this is actually an extremely powerful claim, because what this means is that if in your lab in Cambridge, you're conducting experiments and you determine laws, say how pendulums work, whatever those laws are not unique to Cambridge. Those should be true anywhere in the universe. So this is philosophers nowadays call this the principle of uniformity. The idea that the universe should be understood as a single body operating on the same set of rules. This is a highly controversial claim in 1687. And Newton is also extremely interested in describing or tackling the problem of certainty and what it means to talk about the cause of something. He famously says, hypothesis non fingo, in Latin, which translates to something like, I do not postulate hypotheses. And he's using the word hypothesis here in a slightly different sense than we do today. He's not talking about a general proposed answer to something, but rather the idea of a certain final answer, an absolute truth. So Newton wants to emphasize that you can have truth about the natural world. You can understand important things without it being certain. That is, whatever information you find has to be open to revision and thinking about things further. There's always more science to be done. So all of this comes together in something that's sometimes called the Newtonian synthesis. And the synthesis here is the synthesis of the local, that is things here on the surface of the earth, the experiments you do, with the phenomena that span the entire universe. So it's synthesizing the celestial and the terrestrial. And the classic example of this is his famous law of gravity. Don't panic with the equation here. I'm going to talk us through it a little bit. The equation here is actually quite remarkable, and we should, it's important to remember that equations need to be interpreted like the way poems need to be interpreted. They're not obvious what they mean at a glance. So let's take a moment and kind of think through that. So this F on the left here is force, the force of gravity. Whatever it is that makes the apple fall off the tree, that what you feel pulling you down in your seat right now, that's the force he's interested in. And then we're going to skip to G for a moment. And then M1 and M2, he says, are any two masses in the universe? So the first M might be you. You have some certain amount of mass. And then M2 might be the Earth, has a different amount of mass. And you multiply those numbers together. But the important thing is that they're interacting with each other. And then in the denominator down here, we have R. And R is the distance between those two masses. So in this case, that would be the distance between you and the center of the Earth. So essentially the radius of the Earth here. And the square, this 2 here, means that the force overall drops rapidly as R gets bigger. So since the M's are on top, the bigger the mass, the bigger the force. And the further away they are, the less the force is going to be. Now, the extraordinary thing here is that these anything in the universe is these M's. So in addition to you and the Earth, we also need to think about the mass of you and your cat. right? Your cat has mass as well. And there's some distance between the two of you are. So you can actually calculate the force of gravity between yourself and your cat, and between your cat and the Earth. And the apple on the far side of the room is attracted not just to the surface of the Earth, but also to you. So literally every bit of substance in the universe is pulling on every other bit of substance in the universe and generating some tiny bit of force. Now, some of these R's, the distance between things, are vast. So distance between you and Jupiter is gigantic. So the force seems to be quite small, but it is there, it is present. And distant stars are also pulling on you in this same sort of way. And you can calculate this. Right? This is an extraordinary kind of claim that the universe is held together by these uniform laws. And Newton wants to combine his law of gravity with what nowadays we call his laws of motion. There's a simple statement of inertia. Bodies in motion tend to stay in motion. Bodies in rest tend to stay at rest. An applied force will cause a body to accelerate. His famous simple equation, F equals ma. This is simply a statement that more massive objects are harder to move, and that should be sort of intuitively clear, right? And then every force has an equal and opposite reaction. So when the Earth is pulling on you with gravity, you are pulling on the Earth as well. Since it's so much bigger than you, you don't see the Earth moving very much. But in fact, right now, you are pulling on the Earth, and you are pulling on Jupiter, and you are pulling on distant stars. The universe is this extraordinary cacophony of gravitational forces all pulling on everything else. So what Newton does in the Principia is take these abstract laws, which he arrived at via experiments in his own lab, and then talks through how they could be applied to the universe as a whole. And he says, consider the following thought experiment. So we've got the Earth, and imagine a very tall mountain on the Earth, and you're on top of the Earth with a cannon. And you've put a certain amount of gunpowder in your cannon, and you fire it, and the cannonball moves to the side because you gave it some velocity, and then the Earth's gravity pulls it down. So it arcs a little bit and then hits the ground. So now I put in more gunpowder, so it gets more velocity. It goes a little further before the Earth's gravity pulls it down again. Now I put in even more, and this time it's still being pulled down, but it's moving so fast to the side that it actually kind of gets over the horizon before it hits the ground, but it still does. And he says, if you imagine, there must be some velocity I can give it at which the Earth's gravity pulling down exactly balances its tendency to be going to the side, its inertia, such that it's constantly missing the Earth as it falls and would actually come back around to where it started. And we would call that an orbit. And this is essentially how we would put satellites in orbit today. So Newton says, if you think back to his initial rules of reasoning, if we can figure out how an object here on Earth could be moving in this perfect circle, that must be how the Earth moves in a perfect circle or an ellipse around the sun as well. So it has this same phenomena must explain how it is that the solar system is put together. So this is an utterly unprecedented achievement. It's this precise mathematical explanation and prediction of motion as well. And when Halley sees this, he says, nearer the gods no mortal may approach. So when the Principia presents the Newtonian synthesis, it's uniting the celestial and the terrestrial realms, all of the universe on these same principles. But it's also uniting mathematics and experiment working together in a way that no one had done before. So what Newton has is he has a series of principles, like his laws of motion, that explain the motion of bodies both on Earth and in the sky. And he doesn't have proof in the classical philosophical sense, but what he can do is use his new ideas to make predictions about what the universe would look like if those principles were true. And it turns out that those principles look a lot like the universe we actually live in. So he puts forward what nowadays we would call the hypothetical deductive method, in which you make a prediction about how the universe should be, check to see if that's the case. And then if you see that it is in fact the case, then that's a good reason to think you were right in the first place. It's important to remember that this is now 20 years after his miracle year. Between the miracle year and the publication of the Principia, 2 decades pass. So an important question is, what was he doing in that time? And the answer, strangely, is not mathematics and physics. He essentially, in his miracle year, figures he has solved those problems. What he has spent 20 years doing in the meantime is actually 2 other important things to him, alchemy and theology. And it might seem strange that sort of the greatest scientist of all time spends 20 years doing this. But in fact, over the course of his life, Newton spends more time on alchemy and theology each than mathematics, physics, astronomy, and optics combined. But these are not separate projects for him. And in fact, we see the impact of his work in alchemy and theology in his science as well. So for instance, the very category of force comes out of his investigations in alchemy. So force as a concept is actually very hazy, and this gives rise to all sorts of problems for physics as it develops after him. But it's a very standard concept in 17th century alchemy. The idea that there are invisible, mysterious forces trapped within certain kinds of matter. And it's these forces that let you do things like turn lead into gold and create the philosopher's stone, which will make you immortal and cure diseases and so on. So we know that Newton began studying alchemy at least in 1669. We have the receipt from when he bought his first alchemical books. And that's what convinces him of the reality of forces, that the universe is full of these hidden mysterious things. But he really does spend much of his time doing things like trying to convert lead into gold. And there's a sense in which Newton spends more of his time doing magic than doing experimental philosophy. And alchemy is an intensely secretive practice at the time. You know, he writes his notes in code. We have to reconstruct these things in all sorts of strange ways. But he also did his alchemical experiments on the lawn at Trinity College too. So it's this strange fusion of intensely secretive work that was also weirdly public. Around the same time, he becomes interested in theology, particularly questions of prophecy and biblical scholarship. He's really interested in trying to figure out what the original version of biblical texts said. He's become persuaded by the late 1690s that Christianity, as it's practiced in Europe at the time, was actually a corruption of the existing Christianity, that there was actually kind of a satanic plot to get people practicing Christianity the wrong way. And he wants to recover what he sees as true Christianity, which of course makes him a heretic. In particular, he subscribes to a kind of heresy called Arianism, which denies the divinity of Jesus. And he takes this very seriously, to the point at which in 1675, it becomes required that he has to take holy orders to keep his professorship at Trinity. And this is a standard thing for professors at the time in English colleges to have to do, to take on Anglican orders. But in order for him to do that, he would have to swear belief in the Trinity. And he was not willing to do that, because through his biblical scholarship, he became convinced that the Trinity was incorrect, at least, and probably the result of sort of a conspiracy. So he was actually on the edge of resigning his position and probably having to go live in poverty because he wasn't willing to take this religious oath, when quite suddenly there's a royal dispensation saying that the Lucasian professorship would be the only professorship at Cambridge for which someone would not have to swear holy orders. This probably came about because his old mentor, Isaac Barrow, was an advisor for the king at the time and probably got this to happen. So Newton is spending a lot of time thinking about not just the Bible, but the nature of God generally. And he concludes that thinking about God and thinking about theology is an important part of doing science, or as he says, natural philosophy. And in particular, he sees God as being the explanation for why the laws of nature work the way they do. That is, God sort of maintains the laws of nature, particularly gravity. And we can see the importance of this kind of theological approach by looking at how he addresses a particular technical problem in his astronomical theory, which is what comes to be called the three-body problem. So Newtonian physics works great for two bodies. So if we have the sun and the earth going around it, you can calculate really cleanly and easily why the earth moves in the pattern it does and can show that it'll be stable for long periods of time. The problem is when that third body, say Jupiter, pops up in the system as well, because now Jupiter is pulling on the earth as well as the sun pulling on the earth. And because Jupiter is in motion, the directions of the gravitational pull gets wonky. And you can show fairly quickly that the planets will pull each other out of their orbits and the system becomes unstable. So the three-body problem is, how do you get a stable orbit when you have multiple bodies, at least three, pulling on each other in all different directions? Because it seems to Newton early on that the solar system can't be stable for long periods of time if his theory of gravity is correct, because the planets are all pulling on each other. But he knows that there are astronomical records going back thousands of years suggesting that the solar system is stable for long periods of time. So he has to reconcile the observed stability of the solar system with his theoretical expectation that it should be all falling apart on a regular basis. And his solution to this is God, which is that God intervenes from time to time to nudge the planets back into their correct orbits. But this isn't a sort of, glowing hand coming down and pushing the planets back in. It's too crude for the way Newton thinks about God. Rather, because God spends his time maintaining laws like gravity, what God does is he sends in comets now and then, and the gravitational attraction of the comet on the Earth or the other planets is just right to nudge the planets back in. So in one sort of fell swoop, Newton is able to explain why his theory is still correct, why the solar system maintains stability, and where comets come from. But he says in order to do this, you need to be thinking about the way God interacts with the universe. And this becomes an important kind of practice in British science generally for the next couple of 100 years, which is to think about how God is an actor in the natural world as well. And in particular, Newton wants to have a God that is intervening in the world on a regular basis. He's very interested in refuting this idea that becomes popular in the 18th century called Deism, in which the argument made is that God creates the universe and sort of sets everything in motion, but doesn't intervene, just lets everything run on its own. And Newton thinks that's not a good way of thinking about it. And this clash of differing theological visions culminates in what's sometimes called the Leibniz-Clark correspondence. On the left here, we have the German philosopher Gottfried Wilhelm Leibniz. And then over on the right, we have Samuel Clarke. Clarke is a follower of Newton, something like this. So it's really an argument between Leibniz and Newton, but Newton still doesn't like having public controversy. So he sort of deputizes people like Clarke to have the argument for him. So this is a series of letters back and forth in which Leibniz tries to argue that the best way for God to have created the universe would be in this deistic way, to have everything set up perfectly and running on its own and not requiring intervention. And he mocks Newton for saying that Newton's God has to wind up its watch now and then. And Newton says, what kind of a crummy God have you got that you can't talk to, that doesn't do things, that doesn't intervene? So it's an argument that's sort of simultaneously about physics and theology. It's really a fascinating conversation that goes back and forth. There's an additional layer to this, which is that Leibniz claims that he invents the calculus before Newton, and there's this fantastic priority dispute in which each of them accuse the other of stealing the calculus in a secret kind of way. So in addition to thinking about the nature of God, as I said, Newton's extremely interested in questions of prophecy and the Bible. And what Newton sees as his most important contribution, well beyond the Principia, is calculating the date of the end of the world. That is, Newton looks at the book of Revelations and tries to calculate exactly when this is going to happen. He changes his mind a few times over the years as he does his calculations, but you can see here the kinds of work he's doing. And even though, as I said, he changes his mind about the date, everyone should be reassured that he's quite sure the world is not going to end before 2060. So come the 18th century, the 1700s, Newton becomes famous for his work on mathematics and physics, but he's spending all his time doing alchemy and theology at this point. This is also around when he has what can only be described as a mental breakdown in the 1690s. He begins getting paranoid. He's not willing to talk to people anymore. This is an excerpt from a letter that he writes to his friend John Locke, the philosopher, in which he accuses Locke of trying to get him embroiled with women, in which he says that he hopes Locke will just die for trying to do this. And Newton's friends realize that there's a problem. Something is not going well. They don't know what's wrong with him, but he's behaving very strangely. I should say nowadays we've solved the mystery of why it is that Newton is behaving so strangely at the time. And we're able to solve this mystery actually because of a lock of hair cut off of Newton in the 1690s that is currently still in the Wren Library at Cambridge. So by testing this, we have found that Newton was undergoing mercury poisoning at the time, one of the symptoms of which is in fact paranoia and delusions. I should say mercury poisoning is a very common thing to happen to alchemists because they're working with mercury a lot, and in particular they're boiling it, so you're breathing it in. So this is one of the many reasons to not do alchemical experiments at home. So Newton's friends, of course, have no idea about mercury poisoning as a thing, but they want to bring him from sort of distant Cambridge to London so they can keep a better eye on him. So his friends managed to set up a new job for him, which is running the Royal Mint. So he comes to London, he works on this, he drops his alchemical projects because he can't really do them in London anymore, so he's able to recover slowly. And his friends set him up with the job at the Mint just as a sinecure, just as a job where he doesn't have to do any work. But that's not the way Newton does anything. So he says, if I'm going to be head of the Mint, I'm going to really be head of the Mint. He knows a lot about metallurgy. He redesigns all of the coinage. A lot of the format of modern coins, such as the kind of fluting around the edges, actually tracks back to Newton's resetting the kind of coinage that was being made at the time. And it turns out he also really liked hunting down and hanging counterfeiters as well. At the end of his life, kind of a wonderful moment for him happens, which is that his old rival, Robert Hooke, finally dies. And once Hooke dies, Newton is then willing to go back to the Royal Society as its president. One of the first things he does as president of the Royal Society is order the destruction of all existing portraits of Robert Hooke, which is why we do not know what he looks like at this day. So at the end of his life, Newton is the most famous scientist in the world and is kind of reveling in finally having his work be acknowledged. So 1726, he dies. This is his death mask. This was the thing they did at the time. And he's buried in Westminster Abbey in an extraordinary grave that's actually much more impressive than any of the kings or queens buried in Westminster Abbey as well. And this part of the Abbey is sort of scientist's corner. Down underneath here, this is Darwin's grave. And then a little further below that is where Stephen Hawking is as well. So Newton leaves behind a different kind of culture, what we might call Newtonianism. So it's not just that Newton changed what was known about the universe, and not even ways of knowing about the universe, but also changed what was worth knowing in the universe as a whole. And people were literally rhapsodic about this. So Alexander Pope writes, "Nature laws lay hid in night. God said, let Newton be, and all was light." And in particular, the culture of Newtonianism was one in which it seemed that lawfulness, regularity, rational mathematical regularity was the key aspect of the universe. That was the thing you should know about the universe as a whole. So there's this kind of mechanization of nature, that we should think about everything mechanically and rationally. This gives rise to what we call the Enlightenment. And in particular, there's this goal of trying to find this mechanization and rationality in all aspects of the world, and also in human culture. So for instance, in politics, people say, well, what would Newtonian politics look like? And their answer is it should have an absolute consistency of law. The same way that the universe runs on regular laws, so should our political system as well. Nature isn't arbitrary. Kings shouldn't be arbitrary either. And there's an important sense in which the US Constitution is a model of this, right? It's a balance of forces in the way that the Newtonian universe is a balance of forces. So the kind of universe people are looking for is this one, nature compelled, his piercing mind obeys and gladly shows him all her secret ways. Against mathematics, she has no defense and yields to experimental consequence. I say this is not a very good poem, but nonetheless showing that even poets are reveling in this kind of Newtonian way of thinking about the universe. And what we're left with is what is sometimes called the clockwork universe. Right? The universe runs on these mechanical physical principles in the same way that, say, a clock runs on these principles. So when people talk about the Newtonian universe, this is what they mean, this kind of self-sustaining system. Now, what's bizarre is that this is actually Leibniz's view of the universe, one that is stable and doesn't need intervention. Newton didn't want a clockwork universe. He wanted a messy kind of universe where God had to come in on a regular basis. So perversely, what nowadays we call the Newtonian universe is not at all what Newton wanted to have happen. But nonetheless, that's the image that goes along. So this image of God as the great architect becomes an important emblem for Enlightenment thought. And we see it, say, in the view of the Masons, right? These are architectural tools here explicitly based on the Newtonian idea of God as a great mathematician. Other people suggest that in the 18th century, this idea of a mechanical universe gives rise to the Industrial Revolution, right? Once you start thinking of the universe as a machine, then machines become much more interesting to look at. I should say this view is controversial among historians. But really what it comes down to is that over the next couple of hundred years, everyone wants Newton for themselves. Everyone wants to explain how Newton's ideas in Newtonianism support their idea of how the universe should be. So Voltaire says Newton shows the death of God. Bishop Bentley says Newton demonstrates the necessary existence of God. Kant says that Newton sets up truths that will never be questioned any time in the future, which of course is a great surprise once Einstein comes along. The 19th century domesticates Newton. He becomes a middle-class figure who loves children and puppies. Come the 20th century, as his papers are rediscovered, there's a round of iconoclasm as people discovered that he was more like an alchemist and a magician than he was like a modern. And I think the thing to keep in mind is that every generation reinvents Newton for themselves. So like the founding fathers here in the US, everyone wants to make Newton like themselves, to show that Newton was the first of the people that came to be like themselves. And it's a way of securing authority and validation for our own generation. So, and the stories every generation tells about Newton tell us a lot more about that generation than it does tell us about Newton himself. So thanks very much for your attention. I'm really looking forward to answering your questions. Thank you. Okay, we've got some time for questions now. Thanks so much for sending them along. There's a lot of really interesting things to talk about here. I'll get through as many as I can. Jerry asks when the codes to Newton's journals were cracked and how. It's an interesting thing that in the 17th century, around then, time of say Galileo through Newton, it was actually very common for scientists and all sorts of other people to encode their work. When Galileo first observed the rings of Saturn, he encoded it and published it so he would have a priority, but he wouldn't have to worry about anybody stealing his ideas. All that to say that historians today have a great deal of experience cracking these codes. They tend not to be very sophisticated. So as far as I know, the first person to do that for Newton's journals was the historian Richard Westphal, who wrote one of the great biographies of Newton called Never at Rest. Someone else also asks where his student notebook is kept. Most of the original material having to do with Newton are held at the Wren Library in Cambridge. That's W-R-E-N. If you find yourself in England, it's well worth a visit to visit Trinity College. It's a spectacular place, and then the Wren Library as well. Even if they don't let you in to see the actual documents themselves, there's some fantastic stuff on display. And also a lot of Newton's letters and papers are available online at the Newton Project. That's newtonproject.ox.ac.uk, and a Google search should turn that up too. If you want to read any of Newton's original letters, that can be a lot of fun. Robert asks about Newton's miracle year, as I refer to it. And he points out that Einstein also has a miracle year. His is 1905. And why is it that physicists seem to have these incredible bursts of insight and creativity? And the short answer is no one's quite sure why this is, but it does seem to be a thing that happens particularly for mathematicians and physicists, that they tend to have these really productive years, almost always in their youth as well, when they're fairly young. And why it is hard to say. But it gives rise to all sorts of strange things. So like the Fields Medal is the great award for mathematics, and I think has never been awarded to anyone older than 30. So there seems to be something about the mathematical sciences that gets young people thinking about these things in particularly useful ways. Robert also asks if Newton had not existed, how much longer would it have taken for someone to come up with Newton's conception of gravity? This is an interesting one. There's a thing that often happens in the history of science where all the bits and pieces of a theory are already in place before someone puts them together. So for instance, Newton's law of gravity is an inverse square law. And other folks at the time, like Edmund Halley and Robert Hooke, had realized that there probably was an inverse square force at work, but no one was quite sure how that was going to go. Other people were doing experiments similar to Newton's own, but what he is able to do is bring them all to get all those pieces together in this particularly obsessive kind of way. So I suspect what would have happened was all of the bits and pieces of Newton's theories and ideas would have been there for, say, a generation before somebody connected the dots. And we certainly wouldn't think of it as, say, Newtonian physics. It would be a whole collection of separate ideas. And the same kind of thing happens with Einstein, where all the pieces are there being discussed, even if they're not being brought together in a particular way. Philip asks about whether Newton was aware of the story of the apple falling on his head, or did that appear afterwards? So the beginning of the story is actually Newton's own fault. When he's describing the sort of universality of gravity, he uses as an example gravity pulling on an apple and pulling it out of a tree. And it seems, it can't be a coincidence that he's doing this research while he's in an apple orchard, and that's the sort of image he uses. But the story of him actually seeing the apple fall or actually being hit on his head comes from these 19th century biographies. There's a whole slew of biographies that got written about Newton over the centuries, and many of them are very loose with the truth, I think. So it seems that Newton's mere mention of an apple is enough to create the story, which it does not appear in his lifetime, it appears sometime after. Let's see here. What else have we got here? Jerry asks, what was the basis of his 2060 end of the world prediction? And does anyone stand by this prediction? So figuring out when so I should say, if you're not familiar with it, the book of Revelation is the final book in the Christian Bible. And it's a book of prophecy describing the end of the world as it is supposed to happen. And it's full of all sorts of bizarre and strange imagery that people for, I guess, about 2,000 years now, have tried to interpret as a kind of coded message. That is, if they figure out like what the symbols mean and connect them to historical events, then they can figure out when those events are supposed to happen in future history. So Newton's method for doing that is pretty much the same as everyone's. And this is, I said, this is a long-standing tradition. So people in the 10th century tried to figure out how the events in Revelation connected to the events of their time. And people in Newton's time tried to figure out how the English Civil War was represented in the book of Revelation. And this continues on today. This is the standard sort of thing. And back in the 1980s, people tried to find the Soviet Union in there. In the early 1800s, people tried to find Napoleon in the book of Revelation. So the methods are pretty much the same. I don't know if anyone is particularly attached to Newton's version of that prediction, but as I recall, there's a very healthy Wikipedia page of all the different sorts of predicted dates for the end of the world. Philip asks how physicists today explain the three-body problem and the stability of the solar system. This is a really interesting question. So the stability of, I should say, the three-body problem. I should also mention in passing, that's the name of a fantastic science fiction series that you should go read. It's a little bleak, so beware. There is no solution to the three-body problem in the formal sense that you cannot write down an equation that explains exactly what will happen in a multi-body system like that. Instead, what you do is you come up with a series of approximations that get you better and better answers, even if they're not exact. And this technique was figured out by a French astronomer named Laplace in the early 19th century, right around 1800. And interestingly, so you may remember from my lecture, that Newton saw the insolubility of the three-body problem as sort of a proof of the existence of God. Whereas Laplace was a famously militant atheist. He thought that science showed that God did not exist. So it's quite interesting. Laplace is actually the one to crack the three-body problem. And what he does is figure out a series of equations and methods that let him show that over long periods of time, all those little jitters of the gravity in the solar system, for the most part, cancel each other out. So the solar system will stay stable over tens of thousands of years. And then in the late 20th century, it's discovered that that's not quite complete. And in fact, there's strange circumstances in which a system like the solar system can be stable for very long periods of time and then suddenly become disrupted. And that's the root of what nowadays we call chaos theory. And exactly how it is that systems like the solar system are both sort of stable and chaotic is a really interesting and sort of conceptually difficult thing to grapple with too. Let's see here. Got here. Did Newton show interest in the works of other scientists in other parts of the world, or was he self-centered and unwilling or not interested in others? I think self-centered is a pretty good description for Newton. He was fantastically confident in his own abilities and not particularly concerned about drawing on other work being done. And one of the strange side effects of this is in the 150 years after Newton's time, England develops very different kinds of science than the continent does, because English scientists see themselves as following in Newton's footsteps, essentially, and the continent does not. So they develop things quite differently. So for instance, there's two different versions of calculus, and if you're old enough, you may have learned the English notation of calculus, in which differentials are marked with little dots instead of the ddx notation. So Newton's self-centeredness actually has long-term effects in the way science develops in the world. Let's see. Kathy asks if Newton could have solved the three-body problem if he had accurate masses and distances of the planets and sun. Interestingly, the answer to that is no, that the three-body problem isn't really a question of precision in data. It's a deep problem in the structure of the equations themselves, that they're not solvable in this particular way. And as near as we can tell, it is actually not a solvable problem. So the best thing we can do is have better and better approximations, but the measurements aren't going to help. It's just a question of how clever your calculations are. Let's see. And then Bruce asks, the mathematics of the Principia Mathematica is a geometrical approach, very axiomatic, and why did he choose this approach? He particularly wanted the book to be difficult. There were much easier, so you can write the Principia if you use calculus and more efficient notation, you can write it in about a quarter of its actual size. And in fact, the Indian-American astrophysicist Subrahmanyan Chandrasekhar does this, I think in the 1970s or 1980s, where he rewrites the Principia with modern knowledge, which is really a very ahistorical thing to do, but it's kind of an interesting project. So essentially, Newton chose it to make the book really difficult to show everybody how smart he was. And then I think the question we'll end on here is, could it be that Newton was a high-functioning autistic person or a savant? This is discussed a lot, in particular his sort of social awkwardness and his reluctance to adhere to social conventions and such suggest perhaps something on the autistic spectrum. And generally, this is a hard thing to do with historical figures because the categories we use to develop, that we've developed for use today, for things like, say, mental illness, are very hard to project back onto the past. Without actually interacting with someone, it's very hard to make those sorts of diagnoses. I think it's, in terms of his social awkwardness and inability, Newton's definitely not someone you would want to invite to a cocktail party. All right, and I think we are out of time. Thanks everyone for being here today and your very insightful questions. Take care and be well.